Okay, now we go to the applications of fluorescence spectroscopy. After understanding the principle of spectroscopy, relating it with Jablonski diagram, understanding the radiative and non-radiative emission, okay, we are now at the end of spectroscopy for fluorescence spectroscopy part. Okay, applications will be given to you in terms of what been used in industry, research and development labs, as well as QA and QC application. Okay, most of the time fluorescence spectroscopy is used in biology lab as well, because as I said before, fluorophore is usually used to trace, okay, as a tracer, as a marker for cell, and also for any single cell species. Okay, let us go on the application. What is actually needed for it to be used in any application? Okay, since fluorescence depend linearly on concentration for certain linearity, it can be used to measure concentration just like adsorption experiment. So this is used largely in chemical analysis lah. Okay, while for biology application, they use it as a marker. Okay, linear on concentration for certain linearity range. Okay, when it increase concentration some more, the collision will increase, and therefore the conversion is higher, and then it will decrease again, plateau, and then it decrease. Okay, fluorescence can be used to detect a very low concentration because of the intensity of the emitted fluorescence. Okay, in application, the sensitivity of fluorescence spectrophotometer is at least 10 times higher than UV visible. Okay, so when this is also true, okay, when we couple HPLC, okay, HPLC that you learned last semester, coupled with fluorescence detector, okay, it is 10 times more sensitive as compared to HPLC UV, okay, provided that you are analyzing a native fluorescent compound. Okay, provided that you are analyzing a native fluorescent compound, means that is readily fluorescing. Okay, as compared to a compound that only have chromophore inside it. That's why people manipulate HPLC fluorescence detector because of the high sensitivity. Okay, it is the same thing in spectrophotometer. Okay, this is the fluorescent marker that I mentioned just now. Fluorescent tag is usually used in biochemistry to mark species, okay, single cells, and also sometimes protein as well. When we want to use fluorescence spectroscopy methods, okay, you have to choose excitation and emission wavelength. How do I know this? Okay, you can know what is the excitation and emission wavelength. If it's common compound, you can read inside textbook related to fluorescent. If it's unknown compound, you can scan through the fluorescent spectrophotometer. Okay, so these are some examples. Application, this phenylalanine and tryptophan are native fluorescing compound. Okay, they are readily fluorescing. Okay, means that if you see on the structure, you can have a look in Google. They have at least one benzene ring inside it. Okay, as I mentioned before, vitamin B, riboflavin, it is a yellow, very intense yellow color. When we see is yellow already, and then tocopherol, this is usable, or this is detectable in fluorescent spectrophotometry. Okay, and then we have rhodamine B and fluorescein. Okay, these are some tabulated excitation lambda, emission lambda for several compounds. Okay, See that from phenylalanine to histamine, the excitation and also emission wavelength is increasing. So you can predict that the intensity color from phenylalanine to histamine is increasing as well. We also have application for drugs and pharmaceuticals. Okay, quinine, this is the same with what we did in our journal article active learning. So how does the spectrum of fluorescence look like? So this is a recap. Absorption happen at shorter wavelength as compared to fluorescent. Okay, this is lambda emission. Okay, lambda excitation, or sometimes we call it as absorption. Okay, this is diphenylanthracene in cyclohexane. Okay, now finish about fluorescence. Okay, now we go in a quick outlook towards phosphorescent. Okay, phosphorescent, from the beginning of the slide, I always say that fluorescence is inversely proportional to phosphorescent. If you have high fluorescence, means that the emission, the radiative emission, happens solely in fluorescence. But when you have intersystem crossing, remember Jablonski? When you have intersystem fluorescent, for example, so this is phosphorescent. When you have intersystem crossing, due to several reasons, if let's say you have halogen inside your fluorophore, means that it reduces the fluorescent intensity, but it increase the fluorophore because of phosphorescent, because of the intersystem crossing. Okay, you get more phosphorescent. What happen? You have intersystem crossing. Okay, your first singlet state will become triplet state and then relax to ground state. Okay, rather than you have the singlet state, the different spinning in a molecule, you have now net spin of 0. Okay, so phosphorescent is more favorable with molecule having n to pi star as compared to pi to pi star. This is good for fluorescent, while this one is good for phosphorescent. Okay, when you have n, means that it is aromatic, it still have aromatic molecules, but it is functionalized with carbonyl groups or halide. Remember, in fluorescent, halide is not good in fluorescent, but it's good for phosphorescent. And quantum yield is generally small, very low process, from millisecond, okay, can be up to minute. Okay, the average lifetime is very long. That's why it's good for glow in the dark toy. Okay, phosphorescent. So this is the region where phosphorescence happen. You see that this is triplet state as compared to singlet state in this shorter wavelength. And when you have intersystem crossing, it is actually demonstrating more phosphorescent as compared to fluorescent. So it is depending on your application. Let's say if you don't have any other option of compound, you have to analyze a halogenated aromatic fused ring. So you cannot use fluorescent because fluorescent will give you very low intensity. So you opt for phosphorescent. Okay, in phosphorescent, in order to maintain the phosphorescent radiation, you have to dissolve in a suitable organic solvent. Usually it's ethanol, isopentane, but most of the time it is you can use more viscous solvent, or you can use frozen liquid nitrogen. Okay, whereby in most phosphorimeter, okay, they provide like a Dewa flask. Okay, Dewa flask. Okay, that contain nitrogen inside it. So you put your sample holder, and this one ada nitrogen, liquid nitrogen. Okay, so it looks like this. Okay, so this is the Dewa flask. And then we have rotating chopper. Okay, because of the delayed emission, we don't want the filter to capture anything else other than phosphorescent, because we have to wait for several millisecond and minute, right? So we need to use this chopper. It is actually rotating until when the phosphorescent signal comes out, the emission filter will capture that. Okay, so this is only to show the rotating chopper. This is not to show the filter, because the filter, okay, the monochromator still you have to put it, okay, perpendicular to the excitation. Okay, at least 90 degree. No, sorry, it must be 90 degree. Okay, not more or less than that. See, sample cell over here, there were flash in liquid nitrogen. Sorry, in liquid nitrogen to maintain the phosphorescent radiation. Okay, how does the spectrum looks like? Because it happened at longer wavelength. You see, longer wavelength. It is nearing near IR right now. Okay, absorbance we have one peak. Fluorescent we have one excitation and then one emission. Phosphorescent is even longer at millisecond to minute. Wait, but we can detect this. Okay, so remember back, I said that halogenated fused ring, okay, in fluorescent is not good. Okay, however, it is inversely proportional to phosphorescent. Okay, so this is example of a very good phosphorescent compound. Another one is chlorophyll. Chlorophyll can also emit the radiation at the region of phosphorescent.